So in the last section, we saw that the Fischer projections can be used to represent the structures of our carbohydrates. And in the Fischer projections, we saw that the carbohydrates were all represented as chains. And there were some rules that we followed when we drew and when we interpreted those Fischer projections. So the truth is, when you have a molecule like a sugar that has anywhere from 5, 6, or 7 carbons in it, having a chain is actually less stable than having that chain coil up and actually close to make a ring structure, right? So ring structures are actually way more stable. So ring or cyclic structures are more stable than the open chains. And the way that we represent these ring or cyclic structures is by using this method known as, or by drawing what are known as Hayworth structures. So these are used to represent the cyclic forms of sugars. So the general form that these Hayworth or cyclic structures are going to take are going to look like this structure here that's shown, and these are going to be the most stable forms, like I mentioned, of sugars that are made up of 5 and typically 5 and 6 carbons. And when you look at the Haworth structure, you'll see a couple things. First of all, you'll see that there are OHs and Hs attached to each carbon. So for instance, this carbon here has an OH and an H, and the OH and Hs, they can either be pointing up or they can be pointing down, right? They're either above the ring if they're pointing up, or they can be below the ring if they're pointing down. So there's a carbon here, there's a carbon over here, there's a carbon there, there's another, and then those are the 6 carbons, 1, 2, 3, 4, 5, 6 in this particular sugar. You'll see that some of these bonds here are represented as a little bit thicker than the other. They're thicker lines, and that just is an attempt to represent the three-dimensional nature of the ring. This thick line here means just these bonds are closer to you. So the bonds are closer to the observer. That's all that the thicker lines mean. And the thinner lines, or the thinner bonds, like these ones here that I'm highlighting, these are further away from you. All right, so how do these Hayworth structures, these ring or cyclic structures, actually form in the first place? Well, let's take a look at glucose, D-glucose to be more specific, and see how we can do that. So there's our open chain, our Fischer projection for glucose. It's over here on the left side. What we're going to do is we're going to take this and we're just going to turn it on its side. So we're going to tilt it that way. And what happens is you'll notice that the OHs that were on the right side, the OHs on carbons 2, 4, and 5, they are now pointing down. All right, so, and that's a key thing that you want to keep in mind. So the OHs on the right of the Fischer projection end up pointing down, and that means then that any OHs on the right side, oh, I'm sorry, on the left side of the Fischer projection would be pointing in the other direction, which would be up. All right, so the OH here that was on carbon 3, if we take this open chain and we tilt it to the right, that OH on carbon 3 ends up pointing up. All right, so that's the first step here. And there's our carbon 1, which has the aldehyde on it. And then carbon 2, 3, 4, 5, and 6. So when we tilt it to the right to have our open chain now sort of lying on the side, what happens is the back end of the chain, this region here, ends up folding back around, kind of like the tail of a scorpion. Okay, so the left end of the chain folds around like a scorpion tail. Okay, and what that leads to then is this structure here, or this formation. So we have our tail end where carbons 4, 5, and 6 were located. It ends up folding back around, and what happens is the bond attached to carbon 5 rotates around a little bit, and it brings now that OH here on carbon 5 close to the carbon of the carbonyl on carbon 1. All right, so due to the flipping back around, or the bending of that tail, we end up with the OH, the hydroxyl on carbon 5, becoming close to, or coming close to the carbon of the carbonyl on carbon 1, and what that eventually leads to is a new bond that's going to form between that OH from carbon 5 and carbon number 1, right? And that's the new bond that's formed here. And in order for that bond to form, what we end up doing is this H here, in order for the oxygen to only have 2 bonds, that H gets transferred over to that oxygen to make a new OH, or a new hydroxyl group. And that way the original oxygen here on carbon 5 can have that new bond attached to it. All right, so we end up making a new bond between, let's just write out the numbers. So this is carbon 1, 2, 3, 4, 5, and 6. We end up making a new bond, and then on carbon 1, where that original aldehyde was, the C double bond O, right, this goes away and it gets converted to a regular bond to a hydroxyl, or an OH group. So when we make that new bond now, it actually closes up that ring, and we end up making a 6-sided ring, which we call a Pyranose ring. And you'll notice that there are 6 sides to the ring, but one of the apexes, or apices, I guess, of the ring is actually not a carbon, but an oxygen, right? And that's where that new bond actually is formed right here. So there's a couple of possibilities that can result when we make that new bond. We can end up with either that new hydroxyl group. So this is the new hydroxyl group that's produced. It can either point down, and if it's pointing downwards, we end up with what's known as and that's called the alpha isomer. And if the new hydroxyl group ends up pointing upwards, we call it the beta isomer. All right, so those are two possibilities that can result when that ring closes up. Or we get either the alpha isomer, where that OH on carbon 1 ends up pointing down, or the beta isomer, where the OH on carbon 1 ends up pointing upwards. Right, so this is another case where we have a different type of isomer that can result based on the ring formation or the cycle formation of these sugars. And these ring structures are way more stable than the open chain. All right, so in solution, right, when placed in the when you have a sugar in solution, the predominant form of the sugar is going to be cyclic, right? So you'll have a very, very small amount of it, a trace amount of it in the open chain form where you had that free aldehyde group. The majority of the sugar is going to be in the ring or the cyclic form. So about just over a third of the sugar is going to be in the alpha D-glucose form, and the remaining just under 2/3 are going to be in the beta form where the OH is pointing upwards. All right, and there's an interconversion happening all the time between the alpha D-glucose and the beta D-glucose, and that process is called mutarotation. Which is just the interconversion between the alpha isomer and the beta isomer, right? So that can happen when that chain closes up to form that ring structure. We introduce now a brand new chiral carbon in here, right? So this carbon then, in each of these, ends up being a new chiral carbon in both cases, because it has 4 different groups attached to it. And it didn't before, right? Before that carbon was actually part of an aldehyde group, had a C double bond O. So this is carbon 1, 2, 3, 4, 5, and 6. Carbon 1, 2, 3, 4, 5, and 6. So that can happen when you have an aldehyde group as part of the sugar, an aldohexose in this case. What about when you have a ketone as part of the sugar, as in the case of fructose, right? So remember, fructose is a ketohexose. There's a ketone group and 6 carbons in the chain. Something similar is going to happen, right? So here we are going to take our open chain, we're going to tilt it over to the right side, and then the tail end of it, where carbons 4, 5, and 6 are, these are going to fold back around, okay? And what happens is the OH from carbon 5 ends up coming close to the carbon of the carbonyl in carbon 2. Now, because the carbonyl is on an interior carbon, we end up forming now, instead of a 6-sided ring, we end up forming a 5-sided ring. And the name that we give to a 5-sided ring is a Furanose ring structure, as opposed to a Pyranose that we saw for a 6-sided ring. All right, so if we look at our carbons again, right, so our carbon number 1 had a CH2OH, there it is. Carbon 2 had that carbonyl on it. Now we're going to make a new chiral carbon there, and we're going to introduce a new hydroxyl group. The hydroxyl group here is pointing down. So that makes it the alpha isomer. All right, and then if we go around, there's carbon 3, 4, 5, and 6 right here. And this O here from carbon 5 right? That came from that OH that was originally there. The other thing to note here in the structure that we talked about previously is the OHs that were on the right side end up pointing down. So if you look on carbons, and the ones on the left side are going to be pointing up. All right, so in the case of carbon 3, the OH was on the left side, so it's pointing up. In the case of carbon number 4, it was to the right, and it ends up pointing down. Right, and it's the same case over here where the other option can form, where on carbon 2, where the OH now is pointing upwards. So that means that this is the beta isomer for fructose. Right, so because you do still end up forming a ring, and the ring is going to be the most predominant form in solution, you still have the possibility of it being either the alpha or the beta isomer. 5-sided ring is called Furanose, right? So the way that I remember this, F for 5, F for Furanose, and then the 6-sided ring is the Pyranose, the other one. Okay, so let's just take a look at another practice one here where we have galactose, right? So let's just number the carbons to start off with. So the carbon of the aldehyde is 1, there's 2, 3, 4, 5, and 6. So this is an aldohexose, just like glucose is. The carbons here on the right side are going to be pointing down, and the carbons on the left are going to be pointing up, right? So we can use that as sort of our frame of reference for when we draw our structure, and when we take this and we tilt it on its side. When we tilt it on its side, oops, we end up with our structure that looks like this, right? And if you remember, on carbon number 2, the OH was pointing to the right, right? So that means that it's going to be pointing down. That's exactly what we see. It's pointing down. And then on carbons 3 and 4, the OH was to the left, so they end up going upwards. Then we're going to take the tail end of it, and we're going to flip it around. We're going to sort of do a little scorpion tail on it. So this curls around. And we're going to bring the OH from carbon number 5, this one here, we're going to rotate it around so that it's going to end up being close to the carbon from carbon number 1 that has the carbonyl on it. All right, so again, we end up with our structure that looks like this. So there's our carbon 1, 2, 3, 4, 5, and 6. And there's the OH from carbon 5 that we're interested in. We're going to form a new bond between that O and carbon 1. And this H here ends up moving to this oxygen. So the double bond gets converted to a single, and we stick an H onto that O. So the OH then that's newly formed can either be pointing downwards. So OH down would mean that it's the alpha form, or the OH can be pointing upwards, in which case it is the beta isomer. All right, and if we look at our structure, on carbon number 2, we said the OH was to the right of the Fischer projection, so it's pointing down. And then on carbons 3 and 4, the OH is to the left, so it's pointing up in our cyclic structure.